we were talking about mostly carbon-based nanostructures. So one of the very interesting, like we discussed about fullerene, we discussed about carbon nanotubes, and also graphene. Okay, so these are like the carbon nanostructures which were, so fullerene was one of the first which was discovered in 1985, and then in 1991 so carbon nanotubes were synthesized, and in 2004 graphene was synthesized. And these carbon nanostructures, so really very interesting physical, chemical, I mean all kinds of properties they show. uh, and but all they have very distinct, although the basic building block is always carbon atom, but how the bonding is and how the arrangement, structural arrangement is, that leads to various carbon nanostructures. So when we look at, today we will look at this carbon nanotubes, because this is like one of the, so in carbon nanostructure family, so this is a one-dimensional nanostructure, so like a wire, okay, so like a quantum wire, like one of the best example of like you see quantum effects in carbon nanotubes. But before, so I think there is one some yeah, I think Parameswar has will present something on carbon nanotube in a, so his his term paper topic. Uh, so I'll discuss a little bit of this carbon nanotubes, how the structure is, how you can create different kinds of carbon nanostructures, how you can synthesize, and some of the properties of carbon nanotubes. Uh, so basically, we have three kinds of carbon nanostructures. So one is the achiral and chiral nanostructure, this carbon nanotube. So achiral can be an armchair or a zigzag. So these are the two names given to this achiral carbon nanotubes. And what is the difference between achiral and chiral? So chiral means if you take, or let's say achiral means if you take the mirror reflection, it will be exactly the same. So there will be no change in its appearance. So that is a achiral structure. But a chiral structure will look different under a mirror reflection. Then how one would create these different nanotubes, this armchair or zigzag or chiral nanotubes? So for that we have to actually spread now the carbon nanotube. So basically you can break it and make it like a two-dimensional uh, carbon layer. So like a graphene layer. So it's a two-dimensional layer of graphene, and basically you fold it. So when you fold it, that means you can create like a tube out of it. So you will have a tube axis and a diameter and so on. So you can create a cylinder like hollow structure, and then, so basically this is again a hexagonal lattice. So where we have, so when we look at graphene, so two-dimensional graphene, so you have these lattice vectors a1 and a2. Okay, so this is how you can define your lattice, and by repeating this unit cell, so you can create this two-dimensional structure. So now you can, so each node or each uh, vortex is uh, is a carbon atom, right? So each point is a carbon atom here. Now you can, when you want to make a tube out of it, so you can connect any point. So this point you can connect with this point, okay, or you can connect this one with this one. So when you fold it, okay, so there are basically, so you get three different possibilities, okay. So how you connect the points, these carbon atoms, when you fold it, and that leads to this different kinds of different versions of carbon nanotubes. And so to define, so of course then you can also connect it. So let's say, so in this two-dimensional picture, let's say we have, you can take, let's say, this point O, and now we draw a vector OA. So this is a vector, so which is known as a chiral vector. So now we want to create a nanotube by connecting this point A, or the carbon atom at A, and we fold it and put it at O, so at the origin. And similarly, so this is only one part of the vector, or one part of the tube. So this will basically define your circumference of your tube, right? So now, so just imagine, so I have O and A, that is a vector. So now I want to fold it, and so I put or bring this A to exactly put at O. So that means I can create like a folded structure, and so that will be my circumference of that cylinder, let's say. But you also need to define the tube axis, right? So this is like you have to create a, a unit cell out of it. And so this is your chiral vector, and then you have a translation vector O and B. So this is another vector which defines your translation vector, okay. So these two things, that is what you need to create your carbon nanotube. And then, so that means now, let's say we can create, let's say, and this chiral vector CH and T, the magnitude can be different. So they may not be exactly the same. And so we have something like a rectangle here. So you can say O, A, B prime, and B is a rectangle which you basically fold to create your nanotube. And so this OB vector will define the tube axis, right? And this OA will basically define your, the chiral vector will define your circumference. And the most critical part here is this OA vector, or this chiral vector. And see, this chiral vector, this has a different orientation, it is different from your lattice vector A1 and A2 of your hexagonal unit cell of this graphene sheet, okay. And it contains, let's say, more than one unit cell, in terms of more than one hexagonal unit cell. So you can have more than, like, several number of unit cells, and you can have several hexagonal unit cells within this rectangular block which we have defined. And so how do we then understand what is this OA? So OA, or this chiral vector, you can write it down in terms of this uh, unit, or the lattice vectors A1 and A2. So it has to be some multiple of integer multiple of our lattice vector a1 and a2, right? So if you look at again to the picture here, so this is again, so we are going from one lattice point to another lattice point in the hexagonal lattice, and since a1 and a2 are uh, lattice vectors, so they have to be, so oa has to be a some integer multiple of this lattice vectors. So this is how we can define the chiral vector. And this chiral vector, so this n and m, this integer, this is basically will define your carbon, which kind of carbon nanotube you have. Okay, and so typically if m is equal to n, so that means if the chiral vector, so this is n and n, so it is called a armchair. And if the chiral vector is like you are moving along the one of the lattice vectors, so where m is 0, okay, so in that case it is called a zigzag nanotube. And if n is not equal to m, so it is called a chiral nanotube. Okay, so if we go back to this picture here, so now if or maybe I have a picture somewhere here. Let me just, yeah. So this picture here you see, like now if you move along, like when n, so now let's say we move along this line and you can fold it. So you can fold it from any point. So you can fold it from this point, this point, this point, this point. Okay. So that will create different diameters or different circumference. So you'll have different diameters of carbon nanotube. So this is your zigzag. And why zigzag? So again, you see like this looks like a zigzag, like cross section, and that is why it's a zigzag. So now if you go along this line, so this is where your m is equal to 0, so you are going along the one of the like lattice vectors. Okay, so you are going along this, so this is armchair nanotube. Okay, and this is again, when you look at the cross section, it looks like a armchair like cross section. And similarly, if n and m they are not equal, so it is like a chiral version. So this is how you can distinguish between, so basically these are the three different kinds of nanotubes that you obtain in so you can synthesize. Okay, so we can again do some, like go through a little bit of mathematical like equations so that you can calculate the diameter of the nanotube. uh, so this a1 and a2 vector, like for the hexagonal unit cell, you can define like this. And where a is your lattice parameter, or this, let's say, carbon carbon bond length, which is of the order of 2.4949 angstrom. And if you want to calculate the diameter, so diameter will be the circumference L. So when you fold, so now we have this OA, the chiral vector, and we fold it. So bring the point A to point O, and we bring point B prime to B. Okay. So we have a chiral vector and a translational vector. So we fold it and we create a nanotube. And the diameter will be, you can define the diameter by L by pi. So this is your circumference. And what is the value of L, the magnitude? So it is nothing but the magnitude of this chiral vector, and that will be like, uh, by definition, it will be like a into n square plus m square plus n into m. So again, these vectors a1, a2 are, I mean, it's a hexagonal, so they are not orthogonal. Okay. We can also So another parameter which typically also calculated is the chiral angle. So this angle is basically the angle between your OA or your chiral vector and A1 vector. So what is the projection of this OA on A1 axis? So that is basically you can calculate the angle theta. Okay, so that is the dot product, the inner product of this chiral vector and a1, and you can also calculate what is the angle theta, and you'll see that the angle theta, the maximum angle will be actually uh, 30 degrees, so not more than that. So you cannot have theta larger than higher than 30 degrees. So similarly, we can also define the translational vector t here. So this translational vector, like this t vector, you can also define in terms of this parameters m and n, and the diameter as well. Okay, but the most important parameter is this chiral vector. Okay, so this chiral vector basically defines what kind of nanotube you will have. So one can also calculate. So this ch or the chiral vector defines the diameter, and t, the translation vector, defines the length, right? So that is the length of your tube. So that means this is your tube axis, and this is your the circumference, and this is what you need to define your nanotube. So you can even calculate how many number of hexagons are there within this your this nanotube contains. So you can also calculate that, and that is nothing but your area. You calculate this total area and divide by the area of one unit cell, uh, and and then you can again express it in terms of some numbers. Okay, so all these things you can do. So this table basically is a gives these values for different chiral vectors. Okay, so for example, if you take 5 5, so then you have a diameter of the tube that you'll get is 6.78. Okay, so then you can also so depending on what the tube length that you want, so you can also change the tube length to different values as well. Okay, so why this zigzag or armchair or this chiral structure are interesting? So in fact, the electrical properties depend how or what kind of nanotube structure you have. Okay, so whether it is if it is an armchair, so it is typically it is you will always find it is semiconducting. Okay, so it's a semiconductor. The behavior is like a semiconductor. If you take a chiral structure, a chiral nanotube, so it is almost metallic. But so since n is not equal to m, but if you take a difference n minus m, which uh, is divisible by 3, so it's a 3 times some integer, so this chiral becomes semiconducting. So depending on this, how you fold it, so your carbon nanotube can be a semiconductor or can be a metal. And if you take for example zigzag, so a zigzag is also metallic, similar to like your chiral, but again if your n is 3 times some integer, so it becomes again semiconducting. So this is all due to their density of states that varies depending on what is the diameter of the nanotube, and how you create, like along which direction you fold it, because depending on the, so your uh, uh, your energy level or the density of states. So depends on basically the arrangement of this structure or the crystal structure and how you fold it. So that will give rise to a different structure to your carbon nanotube, and that is basically is reflected in its electronic properties. So you can have a semiconductor or a metal depending on along which direction you are connecting or you are folding your two-dimensional graphene. So this picture again, when we look at, so we have this, like if you go along your armchair, so you fold it along this, so you get an armchair. Okay, and then let's say, so you have this point zero, let's say armchair means, oh yeah, so armchair means n is equal to n, so 0 0, this is 1 1, this is 2 2, this is 3 3, and so on. So now uh, it is, so in this direction it is always semiconducting, right? So this is what the open circle represents, and the closed or the dark circle says whether it will be metal, so now let's say if you, we have a zigzag kind of nanotube and we are going along this zigzag axis, so 0 0 1 0 2 0 3 0. So now as you see, so 0 0 is I mean, of course you cannot make anything out of 0 0. Okay, so now let's say if your chiral vector is defined by 1 0, so it will be metallic, 2 0 metallic, but 3 0 is semiconducting, right? So this is a change from a metallic to a semiconducting. So similarly, 3060 is also semiconducting. But now if you take a, a chiral one, so like let's say we have 2 1, 3 1, 4 1. Ah, yeah. So 4 1 is semiconducting because now the difference n minus m is 3. Okay. So this is why it becomes semiconducting. So these are all kind of uh, studied like for like after 1991 when carbon nanotube was synthesized for the first time. So people then, so in the beginning people were not really the research was did not, or it was not that interesting because it was very difficult to synthesize carbon nanotubes at that time. But then people developed techniques to synthesize them quite easily and with a large amount and with a like a controlled way. And then the research kind of like started, really everyone, almost everyone started working on these nanotubes. And uh, and then all these different structures were created, and their all properties were kind of explored kind of during like 95 or like around up to 2000. Okay, so therefore this synthesis method is actually a very critical part in this carbon nanotube synthesis. I mean, if you want to work with carbon nanotubes, so there are three different techniques actually. Uh, so this is the one here is electric arc discharge. So again, the basic idea here is, and this is the first technique that was developed to synthesize carbon nanotubes. And in fact, this is also in this technique also you get fullerene as well. You also get graphene as well. So that is basically you have the graphite electrodes and then you apply high voltage, so you have an electric discharge. So you have a small gap and you have electric discharge, and in the process you create this carbon nanostructures of, so you can create uh, nanotubes, you create graphene, you also create fullerene. And this technique was, so you have to create a high vacuum and then you have some inert gases. So in the beginning it was helium was used, And as you can see here, this you get like 30 to 50% of multi-wall carbon nanotube. Okay, so in the previous class, we saw that carbon nanotubes can be single wall or can be multi-wall, and mostly you get this multi-wall carbon nanotube in this process. So you also in this process some byproducts are also you get, so nanoparticles here means you get this carbon uh, so fullerene family, from the fullerene family you get nanoparticles. So you get also amorphous carbon nanostructures also you get. So therefore it is not like the best synthesis method for any application point of view. But the most interesting synthesis method or useful for industry is this chemical vapor deposition, CVD. So basically what you have is a chamber, again it's a vacuum chamber, and then you can put some substrate, and then you introduce basically these gases, so methane and these gases, and you heat it up. So basically, you crack your gases, and then you can deposit CNT carbon nanotubes on the substrate. Basically, so in this case, you get mostly pure carbon nanotubes. So not like in the previous case where you have mixture of everything, and therefore you can actually also create these nanotubes precisely on top of your substrate where you want to. So if you want to make a device on silicon, so you can deposit a carbon nanotube precisely on a silicon substrate, and you can make a like a transistor or a field effect transistor or a diode, whatever you want to make out of a carbon nanotube, we can do that. So therefore, this method is quite like uh, standard method for synthesizing carbon nanotubes. Even now, like many 2D materials, you also grow with this CVD process because you have a lot more control and over how you, I mean, you want like a particular structure, so you have a better control in this process. Okay, so that's why CVD is quite used quite a lot in the industrial applications as well. But to deposit something, so you have to identify the proper structure or the proper gas or the precursor that you need. Okay, uh, and sometimes these precursors are also quite, like these are chemical. Okay, and these gases can be very toxic as well. And another method is this laser ablation. So you have again a graphite target, and you put it in a furnace and you expose it to a high power laser in presence of some inert gases, and then you get basically this carbon nanotubes. In this process you also get graphene as well. But this process is, here you get mostly you get this single wall carbon nanotube. Okay, so in other cases you might get single wall or a multi wall, so you are not sure. But in this case you have a higher chances or higher probability that you'll get single wall carbon nanotube. So depending on what you want, so you can choose your technique of synthesis. Uh, yeah, okay. So then, if you look at these, their properties, so electronic properties. So for example, so you will have a different band gap in case of which depends on the diameter of the carbon nanotube. Okay, so the plot here on the left here, it shows that as you increase the diameter, so your energy band gap, so it's a 1 by so inversely proportional. So that means if you increase it, so your band gap will decrease. And so you can tune the optical properties of carbon nanotube as well. So similarly, like what we saw in the quantum dot case, where it is inversely proportional to the diameter. So you can also have very interesting electrical properties. Uh, so we are not discussing all the properties, but you can have very interesting conductivity, electrical conductivity. You can even get a magnetoresistance. So resistance in presence of, so the magnetic field, how the resistance will also change. So you have also a very interesting vibrational modes as well, so mechanical properties. Okay, so many different properties you will have due to this carbon nanotubes, but I think we will not go into any of the application. I mean, if in the future, if we need any particular application and we see if that properties is equal, so we will explore that in the future.